I have a question for you. When was the last time you had to call a customer service line? I mean, really call them.
Oh, don't remind me.
Not a chat bot, but the full, 1-800 experience.
Painful memories. I
Yeah.
tried to cancel a gym membership last month. I think I listened to a looped saxophone solo for about 45 minutes.
That is exactly the circle of hell I'm talking about. You're stuck. You can't hang up because you'll lose your spot. You
Right.
can't really focus on anything else because you have to be ready to jump the second a human voice appears. You're basically paralyzed.
In technical terms, you were blocked.
Exactly. I was blocked. And while I was sitting there staring at the wall, it hit me. And this is exactly how we used to build the internet, and frankly, how a lot of people still build it. You click a button, the server thinks, and you just sit there with the spinner until it comes back.
It's the synchronous trap. It's intuitive because it mimics human conversation.
Yeah.
But it's terrible for scale.
So today, we are going to fix that. We are doing a deep dive into what we're calling the post office of the internet.
I like that.
We're talking about messaging architecture, broker-based APIs, and that wonderful acronym, MOM.
Message-oriented middleware.
Yeah.
It's the infrastructure that stops the internet from acting like a phone call and starts making it act like a global shipping network.
And to guide us, we have this really unique strategic deck. It's based on Learning API Styles by Lucas Stanowski and Marcin Dulak.
And the visuals are great.
Oh, I have to mention the visuals because they are delightful. The whole thing is themed around these vintage bird illustrations.
Yeah, you've got owls, hawks, starlings. It really leans into that whole bird's eye view of system design.
It's perfect.
It reminds us that these messages are literally flying between systems, often over great distances.
So our mission today is to help you, the listener, shift your mental model.
Right.
We want to move you from the call a function mindset to the send a letter mindset. And apparently that shift is the difference between a system that crashes on Black Friday and one that doesn't even blink.
That is not an exaggeration.
Yeah.
If you want to build systems that operate at the scale of, say, Uber or Netflix,
Yeah.
you cannot rely on synchronous phone calls between your servers.
You can't.
You need to decouple them.
Okay, let's unpack that. Slide 2 in our source material calls this the paradigm shift. It contrasts direct contact with mediation.
Right. So let's stick with your phone call analogy. In the standard web world, what we usually call REST communication is synchronous.
Right.
You, the client, make a request to the server. That is a blocking request.
Meaning I can't do anything else until the server responds. I'm on hold again.
Correct. You are tightly coupled. If the server is slow, your app is slow. If the server is down, your app crashes or, throws an error.
You're completely dependent.
You are dependent on the immediate availability of the other party.
Which is fine if I'm just asking what time is it.
Right.
But if I'm asking a system to, I don't know, process a credit card or generate a PDF report.
Then you're in trouble.
Yeah.
So enter the alternative, messaging. This introduces a middleman, the MOM.
Okay.
Instead of calling the server directly, you hand a message to the middleware. You just say, here, take this, and you walk away. It's fire and forget.
The source highlights two massive benefits here. First is non-blocking, which we just covered. I get my life back immediately.
Yep.
But the second one is decoupled. And the source makes a really interesting point here. It says the producer and consumer never even know each other's IP addresses.
That is the superpower for security and maintenance. In a direct connection, I need to know exactly where you live, your IP address, to talk to you.
Right.
If you move, I break.
Mm-hmm.
In a decoupled system, I just need to know where the post office is. I drop my letter in the box. I don't care if a truck picks it up or a drone or a carrier pigeon. I don't care where the processing facility is.
I love that. It sounds cleaner, but it also sounds like it introduces new moving parts. Slide 3 breaks down the anatomy of the system.
It does.
They use a parcel service analogy to demystify all the jargon.
It's a very helpful analogy because the terminology can get dense. So you have the producer, that's you sending the letter.
Okay.
You have the broker. The source uses RabbitMQ as a standard example here. Think of the broker as the post office building itself.
Okay, so I walk into the post office,
Yep.
the broker. I don't just, throw my letter on the floor. I hand it to a clerk.
Right. And this is a distinction that trips up a lot of developers. In this architecture, that clerk is called the exchange.
The exchange. Got it.
The exchange is the sorting facility. It is the router. Its only job is to look at the address on your letter and decide which bin it goes into. It doesn't store the mail. It just directs traffic.
And the bin is the queue.
Precisely. The queue is the mailbox.
What?
It holds the mail until the consumer, the recipient, is ready to come and pick it up.
I want to pause on that because I think it's crucial. The exchange routes. The queue holds.
Yes. If you don't have a queue bound to an exchange, the exchange will just drop the message on the floor. It needs a destination.
And the consumer connects to the queue, not the exchange.
Exactly. The consumer doesn't care about the sorting logic. It just knows, hey, I have mail in my box.
So let's look inside that mailbox. Slide 4 is titled Deep Dive, the queue. And there's a quote here that made me laugh. A happy queue is an empty queue.
It's an old operations proverb. If your queue is full, it means your consumers are falling behind. It's a backlog. You don't want a backlog.
No.
But inside that mailbox, there are strict rules. The most important one is FIFO. First in, first out.
Which is just fair, no cutting in line.
It's more than fair. It's essential for data integrity. Imagine you're an e-commerce site. I place an order, and then 5 seconds later, I cancel the order.
Right.
Those are two messages. If the system processes the cancel message before the order message.
Oh, you try to cancel something that doesn't exist yet, it fails, and then the order goes through anyway and ships?
It's exactly. Chaos. So order matters. The other big rule the source mentions is immutability.
Right.
Once you drop a message into that slot, you cannot reach in with a Sharpie and, change the zip code.
That makes sense. If you messed up, you have to send a new message to correct it.
You do.
But here's the concept that I feel like burns people, the difference between durability and persistence. Because in English, those words mean pretty much the same thing.
They do, but in broker architecture, there are very different settings.
Yeah.
A durable queue means the mailbox itself is bolted to the floor.
Okay.
If the broker crashes, if the post office loses power and restarts, a durable queue will still exist when the lights come back on.
Okay, that sounds good. So my data is safe.
Not necessarily, and this is the gotcha. The mailbox is safe.
Okay.
But if the messages inside it were not marked as persistent, they are gone.
Wait, what? So I could have a perfectly intact, durable queue that is completely empty after a reboot.
Yes, the source explicitly warns. Durable queue does not equal persistent message. Persistence means the message is written to the hard drive. Transience means it lives in memory RAM. RAM is faster, but if the power goes, so does the data.
I can see a developer getting fired over that nuance, but I made the queue durable.
It happens more often than you'd think. You have to be intentional about both.
Okay, so we've built our post office, we understand the rules, now we need to figure out how to actually distribute the work. The deck outlines 5 key patterns.
Right.
Let's start with the absolute workhorse. Slide 5, pattern 01, work queues.
This is the bread and butter of scaling. This is why you use messaging like 80% of the time.
Really?
Yeah. Imagine you have a website where users upload high-resolution profile pictures. You need to resize them, create a thumbnail, maybe apply a filter. That takes CPU power.
And if I do that while the user is on the phone or on the web request?
The site freezes. And if you have 1,000 users upload photos at the same time, your server catches fire.
So instead, we use a work queue.
Right. You accept the upload and say, thanks, we got it, immediately. The user is happy. Then you drop a message into the queue saying, resize image, #123.
And on the other side?
On the other side, you have what we call competing consumers.
Which sounds like a reality TV show.
It does, but it just means you have a pool of workers, let's say 5 servers,
Yep.
all watching that one queue. The broker acts like a card dealer.
Okay.
It deals the messages out, one for you, one for you, one for you. Round robin style.
And the aha moment for me here is the scaling.
Right.
If my site goes viral and suddenly I have 1 million uploads.
You don't change a single line of code.
Yeah.
You just spin up 50 more consumer servers.
Right.
They all attach to the same queue, and the backlog drains faster. It is perfect horizontal scaling.
That's pattern 01. One message, one receiver. But what if I want to be a town crier? I want to shout something to the whole world.
Ah, yes.
Slide 6 brings us to pattern 02. Publish, subscribe.
Or PubSub. This uses a fan-out exchange. Going back to our analogy, imagine you walk into the post office, hand over a letter, and the sorting facility runs it through a high-speed photocopier and puts a copy in every single mailbox in the building.
That sounds incredibly noisy. Why would I want that?
Think about a stock ticker or a weather alert. If the price of gold drops, you want the mobile app, the desktop website, the analytics engine, and the audit log to all know about it instantly. You don't want to pick one. You want one-to-end delivery.
So the exchange completely ignores the address on the envelope?
Completely ignores it. If you are bound to the exchange, you get a copy. But there is a catch mentioned in the source.
Of course there is.
New consumers see only new messages. There's no history. It's like turning on the radio. You don't hear the song that played 5 minutes ago. You only hear what's playing now.
Got it. So if you need history, you need a database, not just a PubSub queue.
Exactly.
Now let's get a little more sophisticated. Slide 7 introduces pattern 03, routing. This uses a direct exchange.
This is selective reception. Now we are looking at the address again. The logic is simple. If the routing key matches X, send to queue X.
The example they give is a logging system. You might have a routing key, like error or info.
Right. It allows you to filter the stream. You could set it up so that your critical error messages go to a queue that writes to a database, because you need to keep those forever.
For legal reasons, yeah.
But your generic info messages, maybe they go to a queue that just prints to a screen in the dev room and then gets discarded.
So you're saving disk space by filtering out the noise.
Exactly. You're decoupling the producer from the storage logic. The producer just says, here's an info log, and the architecture decides it's not worth saving.
That's useful. But pattern 04. This is where I think the real power of messaging unlocks. This feels like the advanced class.
This is fun.
Slide 8, pattern 04, topics.
This is for when exact matches aren't enough. You want pattern matching. We're dealing with wildcards now.
The syntax here is usually words separated by dots, like sensor.usa.kitchen.temp.
Right, and you have two special characters, the star and the hash. Hashtag. The star matches exactly one word. The hash is the greedy one. It matches 0 or more words. Basically, everything after this point.
Okay, I want to test this to make sure I get it. Let's say I have a smart home system.
Perfect.
I'm publishing data like sensor.kitchen.temp, sensor.kitchen.light, sensor.garage.temp. If I want a dashboard that shows the temperature in every room,
You would subscribe to sensor.temp. The star acts as a wildcard for the ream name. It ignores kitchen or garage and just looks for that temp ending.
But what if I'm the security system? I don't care about temperature specifically. I just want to know everything happening in the garage.
Then you subscribe to sensor.garage. Hashtag Witten there. That hash grabs everything after garage. Temperature, motion, lights, door status, all of it.
That is incredibly flexible.
Okay.
Because the person designing the temperature sensor doesn't need to know that the security system even exists.
Exactly. And that is the definition of loose coupling. You can add new features to your system months later, like a new analytics dashboard, just by listening to existing topics. You don't have to touch the original code.
So far, though, all of this has been fire and forget. I send the letter, I walk away. But let's be real, sometimes I actually need an answer.
You do.
Slide 9 talks about pattern 05, request response.
This is the awkward cousin of messaging. Messaging is naturally asynchronous. It doesn't want to wait. So if you need an immediate answer like, did the credit card go through, you have to hack the system a bit.
You have to simulate a conversation using letters.
That's a great way to put it.
Yeah. And you need two queues, one for the request and one for the response. I send you a letter asking a question, and essentially I include a self-addressed stamped envelope for your reply.
But here's the problem I see. If I send out 50 letters to 50 different people and I get 50 replies back in my mailbox, how do I know which answer goes with which question?
That is the million-dollar problem, and the answer is the correlation ID or CID.
Okay.
When you send the request, you stamp a unique ID number on it. The consumer does the work, and when it sends a reply, it must copy that ID onto the return letter. So I'm effectively standing at my mailbox with a clipboard, checking IDs. Reply, hashtag 55 matches, question, hashtag 55.
It's a lot of plumbing. The source includes this pattern because it's possible, but it implies a warning. If you are doing this constantly, maybe you should just use REST.
Just use the phone.
Yeah. You lose a lot of the benefits if you force it to be synchronous.
That brings us to reliability, because if I'm sending money or medical data, probably getting there isn't good enough. Slide 10 breaks down delivery guarantees.
3 flavors. First is at most once. This is fire and forget. It's fast, high performance, but low reliability. If the server crashes the split second after it receives the message, poof, it's gone.
You'd use that for, what, IoT data?
Exactly. Sensor data where another reading is coming in 2 seconds anyway.
Then we have the industry standard. At least once.
This guarantees the message gets delivered. The broker keeps trying until the consumer says, I got it. But there is a catch.
There's always a catch.
If there's a network glitch and the consumer says, I got it, but that acknowledgement gets lost on the way back to the broker.
The broker doesn't know.
The broker thinks it failed, so it sends the message again.
So I get the same letter twice.
Yes, which means your system has to be idempotent.
Great word. Explain that for us.
Idempotency means that if you process the same message twice, the outcome is the same. If I send a message, deposit $10, and you receive it twice.
You can't deposit $20.
Your code needs to be smart enough to see the ID is the same and not deposit $20.
And then there's the third one, The holy grail, exactly once.
Ah, the myth. The source is very clear here. Hard impossible at protocol level. To truly guarantee that a message is processed exactly once, never lost, never duplicated, across a distributed network. The physics of it are incredibly difficult.
It's the two generals problem.
It is. So when a vendor tells you we support exactly once delivery, be very skeptical.
What are they really doing?
Usually they are doing at least once, combined with some very smart deduplication logic in the background. They are hiding the complexity from you, but the complexity is still there.
We can't skip security. Slide 11 lists the fundamentals: TLS, SASL, and ACLs.
It's the standard triad. TLS encrypts the pipe so nobody can read your mail in transit.
Right.
SASL handles authentication verifying who is connecting, and ACL's access control lists handle authorization.
That's the what can they do part.
Right. Just because you are the billing service doesn't mean you should be allowed to read from the HR complaints queue.
Yeah.
ACLs enforce those boundaries.
Moving into the home stretch here, let's talk strategy. Slide 12 brings up documentation. And I didn't know this existed, AsyncAPI.
It's fantastic. If you've ever used Swagger or OpenAPI for normal web APIs, this is that. But for messaging, it treats your messaging interface as a product.
So it documents your channels, topics, payloads.
Everything. And it's so important because messaging is invisible. You can't just hit a URL in a browser and see it working.
Right.
If you don't document your topic structure, new developers will have no idea where to send messages or what format they should be in. It prevents topic soup.
So, after all this complexity, brokers, exchanges, CIDs, idempotency, why do we do it? Slide 13 gives us the strategic yes.
3 big reasons. Loose coupling, we've talked about that.
Yeah.
Teams can move independently.
Yep.
Throughput RabbitMQ can handle like 60,000 messages per second. That's huge volume.
And resilience. This is my favorite one.
Yes. Queues act as shock absorbers. If your database slows down, the queue just fills up a bit, the producer doesn't crash, the user doesn't see an error.
The system bends but doesn't break.
Exactly. It buys you time to fix the problem.
But we have to be honest, there is a strategic no. Slide 14 warns us about the cost.
Don't use a cannon to kill a mosquito. That's the takeaway.
So there's a complexity overhead.
A huge one.
Mm-hmm.
You now have to maintain a broker. You have to monitor it. If that breaker goes down, your whole system stops.
And debugging.
Oh, debugging distributed queues is a nightmare compared to a simple HTTP stack trace. Where did the message go? Why is it stuck in the queue? You lose that linear simplicity.
You can't just follow the code top to bottom.
Not anymore.
So how do we decide? The deck ends with a decision matrix. When do we click install and when do we run away?
The checklist is pretty clear. First, critical delivery. If you are handling financial transactions where dropping data is unacceptable, messaging is safer than rest.
Okay.
Second, decoupled workflows. If you have long-running tasks like that image resizing or generating a PDF, offload it to a queue. Don't make the user wait.
And the third one?
High-frequency data, IoT, trading, clickstream analysis, things that happen faster than a database can write. You need a buffer to catch that fire hose of data.
But if you're just building a simple blog or a to-do list app,
Please stick to rest. Keep it simple. Don't add a post office if you're just handing a note to the person sitting next to you.
we've gone from being stuck on hold with customer service to building a massive, resilient, bird-themed distributed system.
It is a journey. We moved from the rigid synchronous phone call to the flexible asynchronous world of the post office.
And the big takeaway for me is that while the broker is this powerful glue for our systems, it requires a total shift in how we think.
It does.
You can't just plug it in and expect it to behave like a normal API.
It demands respect for the patterns. You have to understand the routing, the exchanges, and the trade-offs between speed and reliability. If you treat a queue like a database, you will have a bad time.
Before we wrap up, I want to leave the listener with something to chew on. We talked about that exactly once, delivery being the holy grail. That's technically impossible at the protocol level.
Right. It's one of those things that keeps senior engineers up at night.
So here's the question I want you to ask yourself next time you look at your code base. If exactly once is impossible for the network to guarantee, how much extra code is currently running in your bank's application layer right now, just to make sure your deposit doesn't show up twice?
That is a terrifying thought. The network can't save you there. Only your business logic can.
Thanks for diving in with us. Next time you see a flock of birds moving in perfect sync, maybe think about the routing keys making that happen.
Or just enjoy the view.
That too. We'll catch you on the next deep dive.